Have you ever wanted to add a breathing light to your own electronics design? Sometimes a product only allows one button and one indicator LED. But that single LED still needs to communicate more than just on and off. It has to show, for example, powering up, standing by, or processing. The easiest solution is blinking. But honestly, blinking feels invasive and cheap. Today, let's break down why a good breathing light is not as simple as it looks. The most common way to create a breathing light is using PWM output from a microcontroller. By increasing the PWM value linearly from 0 to full scale, then decrease it back down to 0, and repeat. For small currents, the MCU pin can drive the LED directly. For higher currents, you add a transistor or a MOSFET. I'm using this LED controller board for demonstration. The MCU is an ESP32. The LED is driven using a MOSFET pulling down, as shown. When the PWM signal goes high, the MOSFET turns on and current starts to flow, and turns on the LED. I wrote a very simple Arduino style example. For every 10 milliseconds, the PWM value increases by 1 until it reaches the maximum, then it goes back down. On paper, this looks reasonable, but let's look at the actual result. As you can see, this doesn't really look like breathing. It looks like a slow and delayed blink. At low brightness, it passes too quickly. At high brightness, it stayed for too long, and not much happened during transition. So what's wrong? At first, you might think this is caused by the LED's nonlinear VI characteristics. But with PWM dimming, the LED current is either full on or full off. So brightness should be linearly related to PWM duty cycle. The real problem is human eyes do not perceive brightness linearly. Our perception is closer to a logarithmic response. We are very sensitive at low brightness and much less sensitive at high brightness. That's why linear PWM feels wrong. A better solution is using a sine wave as dimming curve. A sine wave changes slowly at both ends and faster in the middle, which matches human perception very well. This is the equation to calculate PWM value for each steps with sine wave. For demonstrational purpose, I am using a lookup table for sine wave value. Here I create an Excel sheet to calculate PWM values for each step and create an array to store them. The modification to the code is simple. Just use the original variable as an index to find the desired PWM value in the array. I've also changed the PWM resolution to 10 bits to suit the higher value range. Also, you will want the update interval to be less than 17 milliseconds. This translates into a refresh rate more than 60 Hz to prevent a stepped visual. And here is the result. Now it becomes calmer. The transitions are more significant and evenly distributed. And here is the comparison. Note the one on the left seems to change constantly and evenly, also performs better at each end. Apart from the dimming curve, there's also time resolution. If your brightness update rate is too low, or your PWM resolution is limited, the breathing effect becomes stepped and uneven. Think about a sudden frame rate drop while playing games. A smooth breathing light is not just about brightness, it's also about consistent timing. But in real systems, there are timing stability and performance problems. In simple demos, the breathing effect often runs inside a main loop or relies on delay and timers. That works fine when the system is idle. But once your firmware grows with communication tasks, sensor readings, etc., they might occasionally block into code. the PWM update interval might start to jitter. The jitter might be only a few milliseconds, but to the human eye, it shows up as visual glitches. This is why I recommend using RTOS. RTOS is not about making things more complex. It's about decoupling visual behavior from system workload. By putting the breathing light into its own low priority task and using a stable time base, like vTask delay until, each brightness update happens at a fixed interval, independent of what the rest of the system is doing. Even when other tasks introduce load variance, the breathing effect stays smooth and predictable. In my demonstration, I am using a lookup table to store the PWM values. We can further cut the size of the array in half due to value symmetry, and add some zeros and max in each end to further control the rhythm. This makes it look calmer and relaxing. This works well if you have some extra room space to spare. Alternatively, you can calculate the values at runtime. But floating point math does cost some CPU performance. So in practice, which method to use is simply a trade-off. Alright, this is Thomas, and this is my very first YouTube video. If you found it helpful, feel free to leave a like. In the next video, I will walk you through the design and key considerations behind the LED driver board I briefly introduced earlier, a smart LED controller for indoor lighting that integrates with Home Assistant. Subscribe and stay tuned. Thank you for watching.